Let's start with something very, very simple by describing an isotope. For those of you who study chemistry, this will be an absolute breeze. And actually, for those of you who study physics without chemistry, this will also be an absolute breeze. Let's go. So, nucleons. I think I need to give you a bit of pre-information first. Protons and nucleons are both found inside the nucleus. And you can see my very basic diagram of a nucleus below. Let's say the protons are red and the neutrons are blue. They're both found inside the nucleus, and I hope we all agree on that. As a collective term, we call them nucleons. So a proton is a nucleon and a neutron is a nucleon. Basically, anything that's found inside a nucleus is a nucleon. What we have here is carbon-14. It has 14 nucleons, it has 6 protons and 8 neutrons. If you were to try and represent that on the periodic table, you would have 14 at the top left, C, and then 6 in the bottom left. 6 represents the number of protons, and the number 14 represents the number of nucleons. You can find the number of neutrons by subtracting 6 from 14. Now that is basic nuclear physics, basic notation, and you need to be very comfortable with that before you can proceed with any form of nuclear physics.
And basically what an isotope is you take one element. So in this example, we're going to take carbon. And you look at the different variations of carbon. Now, carbon is always going to have 6 protons because that's what determines what the element is. If you have 7 protons, it becomes a completely different element. It's always going to have the same atomic number. Carbon is always going to have a 6 there. But the nucleon number, or the number of neutrons, can change. You can see here that in this example 1, it has 7 neutrons, in which case it's going to look like this in the notation, because 6 plus 7 is 13. In example 2, it's going to have 6 neutrons, so our notation is going to look like this. And in example 3, it's got 5 neutrons, so our notation is going to look like this. All of these isotopes are still carbon, but they just have a different number of neutrons. And this is the definition of an isotope. It's a substance that has the same number of protons, but a different number of neutrons.
So head to your revision note template and note down the definition of an isotope in the definition section. Now we know what an isotope is, I'm excited because we're about to find out about Einstein's equation, E equals mc squared, the ultimate physics equation. What the heck is it, and what does it mean for the IB physics exams? Let's go and find out.
We'll start with the definition of the atomic mass unit, U. When discussing the mass of a nuclei, it's not really appropriate to use kilograms anymore. Let's take the example of the car. For a car, we'd say it's 880 kilograms. For an atom, we'd say it's 2.01 times 10 to the minus 26 kilograms. Not only is it a bit of a mouthful, but we like to create new units that are more representative of the objects we're studying. So, for example, when we're looking at particles, we use an electron volt as a unit of energy rather than joules. And when we're looking at mass, we use an atomic mass unit as the unit of mass rather than kilograms. And the atomic mass unit is a unit of mass in nuclear physics. It's 1 U is equal to 1.6605 times 10 to the minus 27 kilograms, which is a bit of an odd number. But it's defined as 1/12 of the rest mass of an unbound atom of carbon. So if you were to take an atom of carbon, we'd say that it had 12 U. That means that 1 U would be 1/12 of that. How does that relate then to our more common particles? We have a proton, and in kilograms, the proton is 1.673 times 10 to the minus 27 kilograms. In terms of atomic mass units, it's 1.007276 U. The neutron is slightly more massive than the proton, and you can see that quite well here with the idea of atomic mass units. And our electron is tiny. It's 0.0005486 U. Bearing that in mind and knowing what that now means, I'd like you to consider a helium nucleus. And we're going to pop a helium nucleus in your mind onto a balance. And this can pivot either way, depending on which is the most heavy. When you place the helium nucleus on the balance and everything is joined together and bound together, and then you place its separate components on the other side, it's always the case that the separate components weigh more than the bound nucleus, which doesn't make sense because ultimately we've got 2 protons, 2 neutrons, 2 protons, 2 neutrons, so it should be the same. Something's wrong. Something is missing. There's a mass defect. The mass of the nucleus is always less than the sum of the individual masses of the nucleons, which constitute it. The difference in mass is called the mass defect. So if we take this atom here as an example, the mass of, I think we're looking at nitrogen here, the mass of nitrogen is 14.003074 U, but the mass of its constituent parts is 14.111587 U. It's clearly much greater. The mass defect is the difference between those two numbers. So in this case, the mass defect is 0.108513 U. And what Einstein said was that mass defect, that missing mass, must be converted into pure energy. He said that the mass that is missing from the calculation we did before turns into energy that binds this nucleus together. This doesn't need bound together, so it doesn't need the extra energy. But when it is bound together, that missing mass turns into binding energy. Time for a little bit of actual examiner feedback. Too many candidates gave a loose and ill-considered definition of binding energy. Now, you'll find the proper definitions in this course. All you have to do is learn them, but it's worth noting at this stage, the proper definition for binding energy is the energy required to separate the nucleus into its individual components. What did Einstein do with that thought? He said that the missing mass turns into binding energy. And he came up with a very famous equation. He said that the change in energy, the binding energy, is equal to the missing mass, the mass defect, times c squared. E equals mc squared. And I'm sure you've heard that before. Let's have a look at this in use. Calculate the binding energy in the nucleus of nitrogen-14. So we have this missing mass. That one weighs less than that one. So the missing mass is 14.111587 U minus 14.00074, which gives us a change in mass of this. We want to pop that into E equals mc squared, but we need to change it into kilograms first. So we change it into kilograms, times it by 3 times 10 to the 8 squared, and we come out with 1.62 times 10 to the minus 11 joules. I'm not sure how happy I am with that because we've had to go back to kilograms and we've had to go back to joules. It seems a bit messy. And what we really want to do is we want to use atomic mass units and mega electron volts. Let's have a look at this mass energy conversion. It's not always convenient to use E equals mc squared. In nuclear physics, mass is quoted in atomic mass units, not kilograms. And similarly, energy is quoted in mega electron volts, not joules. So what we can do is we can take pretend we have a mass defect of 1 atomic mass unit, And we can pop that mass defect into this equation and find out what the equivalent binding energy would be. So if we have one atomic mass unit, we'll turn it into kilograms, we'll pop it into here, multiply it by 3 times 10 to the 8 squared, and we get this amount of number. And we can find out how many mega electron volts that is. But going forward, it's much easier for us just to say that one atomic mass unit is equivalent to a binding energy of 931 mega electron volts, which makes things a lot simpler because we can use that much, much quicker. Here's a question. Calculate the binding energy in mega electron volts in the He4 nucleus. So we have the constituent parts are greater in mass than the nucleus, and it's greater in mass, let's go to the answer, by 0.030346 because we've just subtracted that from that. Now, instead of turning it into kilograms and then popping it into E equals mc squared and then finding out how many joules it is and then turning it into mega electron volts, we can say that one atomic mass unit is equivalent to 931 mega electron volts. So we just simply multiply 931 by that number there, 0.0304, and that tells us that that mass defect is equivalent to 28.6 mega electron volts. That's the binding energy there. It says you're using E equals mc squared. You don't have to use it at all. It kind of makes sense that a larger nucleus would have a greater binding energy. Let's think about that because say you're looking at uranium. It's got 93 protons, 235 nucleons. It's going to need loads of energy to pull that all together. In helium, you've only got 2 protons and 2 neutrons. It's not going to need as much energy to pull that together. But that is not an indication of how stable the object is. The stability of the nucleus, how likely it is to stay as it actually is determined by the binding energy per nucleon. So how much energy does each individual nucleon have? Let's look at an example. Helium-4, it has 4 nucleons. The binding energy of the total nucleus is 28.6 mega electron volts. So we divide that by 4, and that means that each nucleon has 7.15 mega electron volts. Now look at, say, nitrogen-14. The binding energy of the whole nucleus is 101 mega electron volts. So you'd think that nitrogen must be more stable than helium. But to make a true comparison, we need to work out what the energy per nucleon is. So we divide 101 by 14, and we find the binding energy per nucleon is 7.22 mega electron volts. So yes, nitrogen is more stable than helium, but it's not always the case that bigger atoms are more stable.
Great, we've done a brief but thorough introduction to E equals mc squared. We've done a few examples to make sure we know how to use it. And what I'd like you to do is note down the following. Note down the definition of binding energy and binding energy per nucleon, because the examiners have mentioned to us that that is a failing of previous IB students. Memorise that one atomic mass unit is equal or equivalent to 931 mega electron volts, because that's not given in your data booklet, but it makes answering questions oh so much easier. And finally, take some time to make your own notes on Einstein's mass energy equivalence. When we're considering binding energy per nucleon and we're looking at all the different elements and isotopes in the periodic table, it's really useful to look at a graph. And actually, this graph is really common in exams and it's really interesting. So we're going to look at the general shape of the graph for the average binding energy per nucleon against nucleon number. Let's go.
If you take every atom, every possible isotope, and calculate their binding energy per nucleon, you end up with a graph that looks a little bit like this. Here we have the number of nucleons across the bottom, so the numbers of protons plus neutrons in the nucleus. And on the y-axis, we have the average binding energy per nucleon. And you can see that very small atoms, so hydrogen, helium, boron, carbon, that sort of thing, they have quite small binding energies. They're not very stable. And what these nuclei do to become more stable is they undergo nuclear fusion. As we go through the nucleon number and get greater and greater nucleon numbers, so atoms that have greater numbers of protons and neutrons, the stability of the nucleus seems to improve. So the most stable atom is actually iron 56. Nothing will happen to that atom, that nucleus. That will stay like that forever. It's very, very stable. But as you increase the nucleon number, they get less stable. The average binding energy per nucleon decreases, which means it's less stable. And these larger nuclei undergo nuclear fission to become more stable. Time for a bit of actual examiner feedback. Candidates were poor at recalling the shape of the graph of binding energy per nucleon against nucleon number. So please do have a rough idea of what is on either axis of this graph, but also the rough shape. You can see there's a point here where we've got helium-4, which is very stable, goes down to lithium, and then we reach the greatest stability point at iron. It is worth remembering the shape of that graph and understanding that wherever your atom or nucleus lies on this graph tells you how stable the atom is. Hydrogen 1 is very, very unstable. Uranium is less stable than xenon. Xenon is less stable than iron. Carbon 12 is more stable than nitrogen 14. In fact, if we're looking for a pattern of stability, then it's fair to say after the most stable nucleus of iron, we can see that the binding energy curve is not really a curve anymore. It actually tends to plateau out. The binding energy per nucleon after around about number 60 is approximately constant. Let's head to our revision note template. I'd like you to draw and annotate the graph of binding energy per nucleon versus nucleon number. You'll notice that I mentioned fusion in that graph. I think I mentioned radioactive decay and fission as well. If not, it's a little bit of a teaser as to what's to come. Okay, so this graph is the fundamental point that we work from: fusion, fission, and radioactive decay. So it is important you understand it. From looking at binding energy, we can see that some nuclei are more stable than others. But why? Why are some nuclei just unstable? And that is down to the strong force. Let's delve into that a little bit more. Consider 2 protons inside a nucleus. Of course, we know that there's more than 2 protons inside a nucleus, and we know that there's neutrons there as well. But let's just have a look at 2 protons for the moment. Both of those protons will be closely packed together. They will both have a positive charge, and they will both have mass. That means that both protons will be subject to the electrostatic force. They will both feel a force because of their electrostatic charge. And they'll both feel a gravitational force because they both have mass. And being clever IB physics students, we know how to calculate the size of that force. So if we look at the size of the electrostatic force first, it's 2 charges. We can calculate the force between them by simply using Coulomb's law. And I've done that already, and we pop in the numbers. And we have a repulsive force. They're going to be pushed apart with a force of 57.5 newtons. Fine. They're going to be pushed apart with that force. We then look at the gravitational force because they both have mass, and we can use Newton's law of gravitation to calculate the attractive force. And when you pop in all the numbers, the attractive force is only 4.7 times 10 to the minus 35 newtons. That means that they should be blowing apart because the gravitational force is not nearly attractive enough to balance out the repulsive force. So there must be another force of attraction within a nucleus that's not electrostatic and that's not gravitational. And that's where the strong force comes in. The strong force is an attractive force inside a nucleus
within a very small range. So within the range of about 0.5 femtometers, so which is 10 to the minus 15, and 2.2 femtometers, we have a very strong attractive force. After 2.2 femtometers, the strong force is zero. So it doesn't act at all after this distance. And the typical separation between nucleons within a nucleus is, by chance, hits exactly on where the strong force is the most attractive. So the strong force is highly attractive between two protons within 1 to 2 femtometers, and it's repulsive when the two protons are at smaller separations, so they can't overlap each other. And it's extremely short range. It has no effect outside the nucleus. So the strong force is the reason that these two protons don't fly away from each other. Before we head on to the next section, I'd like you to take some time to note down what we've just learned about the strong force and unstable nuclei. I'd also like you to complete question 5 in your knowledge questions. And I think life's going to be a lot easier if we start with the basics. What is radioactive decay? How is it measured? And what is activity? Because those fundamental concepts will allow us to really fully understand the whole topic of radioactive decay. So we know that the strong force holds the nucleus together, and the energy associated with this force is called the binding energy. But if you imagine that we have all these protons in the nucleus and lots of neutrons, the natural state of order is that the protons will be pulled apart because of the neutrons there. And in an unstable nuclei, the strong forces do not generate enough binding energy to hold the nucleus together permanently. And these unstable nuclei are radioactive. So radioactive nuclei, or radioactive isotopes, are when the strong force cannot generate enough binding energy to hold it together. And when that happens, to make it more stable, so when an unstable nuclei or an unstable isotope it becomes unstable, it wants to become stable. It wants to lose some energy or lose some particles so that it can become stable and be left alone. We call the unstable isotope, we call that the parent isotope. And then once it's released a particle to become more stable, we call the remainder product a daughter product, and that is stable. Now, to become more stable, it spontaneously emits an alpha, beta, or gamma particle, and it becomes a daughter product with a higher stability. One really important fact about radioactive decay and this process is that it's random and spontaneous. It naturally occurs. You can't do anything to influence it. You can't put a magnetic field near it. You can't heat it up. You can't increase the pressure. If this parent isotope wants to release a beta particle under its own steam, it will do so. You can't make it do it. It's naturally occurring, it's random, and it's spontaneous. So we can't influence at all with heat, pressure, or magnetic fields. And we don't know when it's going to happen. Because it's random and spontaneous, the frustrating part about that for us physicists is we like to model stuff and we like to know exactly what's going to happen. And radioactive decay is something that's frustrating because we can't model it. We can model it, and we'll talk about that later, but we can't know exactly when any unstable isotope is about to decay.
How do we know that something has given off radiation? Well, it's invisible. Unfortunately, unlike The Simpsons, it does not glow in the dark. We don't know if something's radioactive or not. So we do rely on detectors to measure the radioactive decay. And you've probably seen this one in your class. This is called a Geiger-Müller tube. And you hear little dots or beeps every time a bit of radiation is identified. It's also recorded on this counter here as well. A Geiger-Müller tube. Do you recognise the name Geiger? He was part of the Rutherford scattering experiment. And the other more traditional way to do it is to use photographic paper. If you place a radioactive material on top of photographic paper, then it causes the photographic paper to become exposed. Activity. Activity is the term we use to talk about how radioactive something is. The release of a radioactive particle from an unstable nucleus is random and spontaneous. But what we can do is we can measure the count rate. We can measure the number of decays recorded each second by a detector. So we can, using our Geiger millitube, we can record the number of decays every second using this detector. And we measure how much that count rate is by something called activity. And activity is the rate at which a source of unstable nuclei decays. And in simple terms, that means it's the number of decays per second. So activity is the number of times per second a radioactive isotope gives out radiation, and it's measured in becquerels. 1 becquerel is equal to 1 count per second. 10 becquerels, guess what? 10 counts per second. And so on. So the activity is a measure of how much radiation is being given off, and it's measured in becquerels. We go to our other notes section, and we'll describe radioactive decay and write down the definition of activity.
That covers the basics. Let's head to your revision note template, go to the other notes section and describe radioactive decay, also write down how it's measured, then head to your definitions section and define activity, including the units of becquerels. Moving on to the different types of radiation, we'll be looking at alpha, beta and gamma radiation. I'll show you how to complete decay equations for each type of decay, and we'll look at 2 types of beta decay, beta minus and beta plus, which then explains the existence of neutrinos and antineutrinos. So this unstable parent isotope undergoes a decay process, and it either gives out a helium nucleus, which we call an alpha particle, and an electron, which we call a beta particle, or it gives out a photon, which we call a gamma particle. And we're going to talk through the properties of alpha, beta and gamma particles right now. And this is where I'd like you to fill in the table that we have on the worksheet. So you have a table with the accompanying worksheet that looks like this. You can see there's a column for alpha particles, a column for beta particles, and a column for gamma particles. I'd like you to fill out the column as we talk through the properties in the following slides. So get your table ready, please. Let's start with alpha particles. When a parent and an unstable nucleus releases an alpha particle, it turns into a daughter product. That daughter product tends to be more stable. What actually is an alpha particle? Well, the nature of an alpha particle is a helium nucleus. If you think about helium, it's got 2 protons, 2 neutrons, and then 2 electrons flying around it. But a helium nucleus, if we talk about the helium atom, then it's electrically neutral because the 2 electrons balance out the 2 protons. As soon as you remove the 2 electrons and just look at the nucleus, then it becomes charged because it's got 2 protons and nothing to balance it out. So our alpha particle is formed of a helium nucleus, but it's also highly ionizing. And what that means is these little alpha particles will fly about in space, and they've got a positive 2+ charge, and they're desperate to attract some electrons to neutralize themselves. So actually they can grab electrons from surrounding gases or surrounding other atoms to neutralize themselves, but what that has the effect of is it then ionizes the other atoms, which means it has an ionizing effect on anything that goes around it. So alpha particles are highly ionizing. It has a very weak penetration. So if you were to release an alpha particle into the air, it would actually only travel a few centimeters before it was absorbed or it became a helium atom. So whilst it's highly ionizing, it actually only gets a couple of centimeters in the air. So it's not that dangerous for humans if it's outside the body because it can't penetrate through the skin. And, you can stand next to an alpha source. You can stand a meter away and actually none of them would reach your body. So if it's outside the body, alpha radiation is not dangerous at all. However, if you ingest alpha radiation, so if you take it inside your body, which is what they think all these Russian spies have done, then it is highly ionizing and it's extremely dangerous. So my advice to you is do not ingest any alpha radiation. Okay. It travels relatively slow. Now, I know that 15,000 kilometers per second sounds quite fast to you, and it is fast, but in terms of particle physics, actually it's quite a slow, heavy, cumbersome particle. So it's a relatively slow particle. And finally, because we're looking at protons and neutrons, it is governed by the strong nuclear force. We talked about that strong force earlier as being part of a nucleus. So when we're looking at alpha particles, it's governed by the strong force. Can you make sure that these 6 points are currently inside your table? Could you also make sure that you copy down this decay equation, the uranium, thorium and helium decay equation, into your table? I'm going to keep on this slide, but if you look at the decay equation above, you'll notice that the nucleon number, which is on the top line, has gone down by 4. And the proton number, which is on the bottom line, has gone down by 2. On the left-hand side of the arrow, we have 238 nucleons. And on the right-hand side of the arrow, we've got 234 plus 4, which is 238 nucleons. And on the left-hand side of the arrow, on the proton number side, we have 92. And if you add 90 plus 2 on the right-hand side, we have 92. So it's completely balanced. Your aim for when you are completing a decay equation for an alpha decay is that it's completely balanced on both sides. This 2 plus is there to put you off. Ignore it, okay? Means nothing. Now we move on to beta minus decay. So we have a representation of it here. We've got the parent nucleus, which is unstable. It transitions into a daughter nucleus, which is more stable. And in the process, it gives off an electron and an anti-neutrino. The reason this is called a beta minus decay is because the electron is minus. So beta minus decay gives off an electron, which is minus. We'll talk about the beta plus decay shortly. We have an anti-neutrino on the end. Can you see that? It's a sort of slanty V with an E on the bottom, and it's got the bar across it, which means anti. So that is the symbol for anti-neutrino. And whenever you have to write down a decay equation for beta minus decay, you have to always put this anti-neutrino on the end. So the nature of beta minus decay is an electron. Where does that electron come from? Let's pop this section into your extra notes section at the bottom of your table. The neutron turns into a proton and electron. I'm going to talk about that process in a little bit more detail in a second. Then the electron is ejected. The proton stays inside the nucleus. And this only occurs in a neutron-rich, unstable nuclei. So if there's more neutrons than there should be inside this unstable nuclei, a neutron turns itself into a proton and electron and fires out the electron. So what that means is, if you look at the decay equation above, because a neutron is turned into a proton, the number of nucleons remains the same. So the nucleon number at the top doesn't change. But because a neutron has turned into a proton, the proton number goes up by 1. Now, it's really important that that decay equation still balances. So if you look at left-hand side of the equation and the right-hand side of the equation, they still balance. At the top, we've got 1 and 1, and at the bottom, we've got 0 and 1 minus 1, so 0. So the equation still balances. It's just that the nucleon number has not changed. That's on the top. But the proton number has increased by 1. And that's going to be super important for you to remember as you're doing beta minus decay equations in SAS. A beta minus decay has less ionizing energy. It is still ionizing because it's got a 1 minus charge. So it is going to be attracting other charges towards it. And it is going to have an ionizing effect, but it's less ionizing than the alpha particle. It's got a greater penetration than alpha particles. It actually penetrates a few centimetres of aluminium. So it's harder to get away from beta particles. It's more hazardous to humans as well because it can penetrate our skin and it is ionizing. So it's one of the more dangerous radioactive materials to us. It travels very quickly. It travels close to the speed of light, and that's because the electron has practically no mass. Well, it does have mass. It's got a mass of 9.1 times 10 to the minus 31 kilograms, but that's tiny. So it travels really, really fast. And it is governed by the weak nuclear force. So the alpha particle is governed by the strong force, but the electron, or the beta minus decay, is governed by the weak nuclear force. I think I would pause the video if I were you right now and add this to your table. Okay, so the next type of beta decay is the beta plus decay. And you'll notice some really huge similarities in this type of decay. So we have, first of all, instead of, you'll notice earlier it was an electron and an antineutrino coming out. This time you'll notice it's a positron and a neutrino being ejected. So the total opposites of the ones before. So the nature of a beta plus decay is that it's a positron. And in this case, it's a proton that turns into a neutron and a positron. The positron is ejected, and this only occurs in proton-rich unstable nuclei. So if you have an unstable nuclei that's got too many protons, this is a kind of decay that happens. Again, a beta plus decay has less ionizing charge. It's a 1 plus charge, so it's dangerous to us, but not as dangerous as alpha. It has an average penetration, so again, it can penetrate a few centimetres of aluminium. It's more hazardous to humans because it can penetrate our skin, and it travels very quickly, close to the speed of light, and it's governed by the weak nuclear force. So all of the properties of beta plus are exactly the same, except for it is the polar opposite in terms of how it's created. Moving on to gamma, our final type of radiation. Gamma is not actually a particle, it's a high energy photon. You'll have heard of gamma radiation when you studied the electromagnetic spectrum. So we've got radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. And gamma rays are photons at the highest energy of the electromagnetic spectrum. So what happens is when we have an excited nucleus and it decays into a lower energy level, it releases the extra energy as a gamma ray. The atomic and mass number of the nucleus is exactly the same once it's turned into the daughter nucleus, but it forms a different energy state of the same element. So it's kind of like an electron jumping between energy states. This is what happens with the nucleus. It jumps between energy states. So it releases energy in the form of a gamma ray and moves to a different energy state. All the actual physical details of it, the number of nucleons, number of protons, are all the same. There's no electrical charge on a gamma ray because it's a photon. It has a very strong penetration, so it's a few centimetres of lead. So when we look at looking at nuclear power, actually the daughter products of nuclear fission are radioactive. And what we do with the waste is we put them in very, very thick lead boxes because the lead absorbs the gamma radiation from nuclear waste. And I don't know what they do with them after that. I think they probably shove them at the bottom of the sea somewhere near Russia or something. I don't know. Maybe they put them somewhere secret. I have no idea where it all goes. But it's highly radioactive, and that's why they put radioactive waste into lead, because it absorbs the gamma radiation. It can easily pass through the human body and can damage cells. So whilst it's not ionizing, it's got extremely high energy, and that can damage our body cells. And it travels at the speed of light. So there is the information about gamma radiation. Pause the video now and pop it into your table. Given all that information about alpha, beta minus, beta plus, and gamma radiation, the first page of your extra worksheet, and that's the table we've been working on, should be full and ready for you to learn all that information. It's just a hard fact that this information is needed to be memorised to make sure you can answer properly the questions on radioactive decay. The next few learning objectives lead us into something called the half-life of radioactive decay, and we're going to undertake an activity as we watch this tutorial to make sure you properly understand how to address these two learning objectives. What we're going to do now is we're going to model the idea of decay. So we're going to take the idea that there's unstable nuclei and they release an alpha, beta, or gamma particle to become stable. And we're going to look at that in more detail. So for that, you're going to need your table in front of you. It looks like this in your handout. So can we have that table in front of us? And I have here, it's a model, obviously, but let's say we've got 50 unstable isotopes. Let's pretend that this is a big bit of uranium and we're looking at a small part of it, and there's 50 unstable isotopes in that uranium. And every 10 seconds, we're going to look at this part of the uranium and we're going to determine how many are unstable and how many have released an alpha, beta, or gamma particle to become stable. So in your table right now, at 0 seconds, we can see that there's 50 unstable nuclei and there's 0 stable nuclei. So no radiation has been given off at this stage. Can I ask you to write that into your table right now? And I'm turning my timer on. And every 10 seconds, I'm going to show you what's happened to these unstable nuclei after 10 seconds. So I'm going to start the timer now. We're at 5 seconds. So let's see what happens in 5 seconds, at 10 seconds. So after 10 seconds, you can see that we have 31 unstable nuclei. That means that 19 of them have given off alpha, beta, or gamma radiation and become stable. After 20 seconds, we're at 18 unstable and 32 have become stable by giving off radiation. At 30 seconds, we have 11 unstable. That means 39 have given off radiation. At 40 seconds, we have 6 unstable, so it's really decayed quickly. At 50 seconds, we have 4 unstable. And we have 46 stable. We're going to go up to 100 seconds. At 60 seconds, we have 3 unstable and 47 have given off radiation to become stable. At 70 seconds, we have 2 unstable and 48 stable. And at 80 seconds, we have 1 left that's unstable and 49 have given off their radiation to become stable. At 90 seconds, which is now, we still have that 1 unstable one. It's taking ages and we don't know when it's going to happen because it's spontaneous. It's random. We can't tell when it's going to happen. Let's have a look what happens at 100 seconds. It's gone. So they've all given off their radiation and 0 of them are unstable now. Now, I hope we were on the ball there because I hope we were adding to your table, the values. If not, I'm going to go back through them. So, pop the values in your tables now. At 0 seconds, it was 50. At 10 seconds, it was 31. At 20 seconds, it was 18. At 30 seconds, it was 11. At 40 seconds, it was 6. At 50 seconds, it was 4. At 60 seconds, it was 3. At 70 seconds, it was 2. 80 seconds, it was 1. At 90 seconds, it was 1. Now, you have your table there, and you have instructions underneath that table to plot a graph. I would like you to plot a graph using the graph paper provided of the number of unstable nuclei on the y-axis against the time on the x-axis. And I want you to follow the instructions to find out what the half-life of that substance was. I want you to pause the video now. Now, I'm assuming that you paused the video and plotted the graph. And if you didn't, then do you know what? This is not how it works. You have to do the work to ace your IB physics exams. So if you didn't do it, go back and do the work. If you did do it, well done. I'm pleased to have you here. What you can see is I follow the instructions on the worksheet, and we now have an average half-life of 15 seconds. So if we look at the definition of half-life, it's the average time taken for a substance to fall to half of its initial value. Well, we use the term average because it's a random and spontaneous system. So we can never say it's exactly 15 seconds every single time. It might, in this case it is because it's a mathematical model that I've just used. But you might have 14 seconds and then 17 seconds and then 12 seconds. So you have to take the average value of those. Let's keep going. Let's keep working. Head to your revision note template and define the half-life of a radioactive substance in your definition section. Go to your common graphs section and draw an example graph of radioactive decay, which shows that very special exponential decay curve, and annotate that graph showing how you would find the half-life of a radioactive substance. And finally, complete questions 7 to 10 in knowledge questions.
Did you know that as you sit exactly where you are, you're actually being exposed to radiation? If you had a Geiger counter sat on your desk right now or right beside your phone, it would be beeping because there is something called background radiation, and it is everywhere around us. And by the end of this little short session, you'll know exactly what background radiation is, but you'll also understand why background radiation is greater in some places than it is in other, and what factors affect that level of background radiation. What is background radiation? Well, the definition of it is that it's a low-level radiation all around us all the time. And right now we're going to talk about the natural sources of background radiation. And believe it or not, rocks and buildings are a natural source of background radiation. Rocks and buildings contain radiation. Some escapes into the atmosphere, but most of the radiation is absorbed by those rocks. Food and drink. If you have a really high diet of shellfish and Brazil nuts, they're highly radioactive, and that will increase your exposure to background radiation. Radon. Radon is a gas that's found in the Earth's atmosphere, and it's produced in the rocks, and it seeps out of the ground. Depending on where you live, depends on how much radon is in your air. And finally, another source of natural background radiation is cosmic radiation. It comes from space. Now, what the atmosphere does, amongst many other things, is it does absorb much of this cosmic radiation. But if you go above the atmosphere, or closer to the top of the atmosphere by flying in an airplane, you get exposed to more of this background radiation. There's also man-made background radiation as well. So this low-level radiation that's around us all the time, not all of it is natural. Some of it is man-made. So if you have a country where nuclear weapons testing is routine, you would find the background radiation is a little higher there. Or if you live near a nuclear accident, like Chernobyl or Fukushima, then you would be exposed to greater levels of background radiation. And this is a picture here of Chernobyl after the Chernobyl disaster, and you can see the effects that the radiation and the explosion had on Chernobyl. But also what happened longer term was that the people who lived there had greater exposure to background radiation and a greater chance of cancer. Now, one of the things that's really interesting to do is to work out what your dose of background radiation is. And there's a little sheet attached to the bottom of this tutorial, and you can actually tick off and work out what your dose of background radiation is per year. And it depends on a number of things. It depends on where you live. So, do you live near a region of radon rocks? And if you look at this map here underneath me, you can see that Cornwall has quite a high count rate of radiation. So the rocks in Cornwall seem to be highly radioactive. If you live in Cornwall, your background radiation will be higher than, for example, if you live in Glasgow up here. Now, I live here in Edinburgh, so I think I'm okay. Do you live high above the sea level? So you can see that some places here up in the Highlands, for example, these are high above sea level, so perhaps more exposure to cosmic radiation. So that will increase your chances of increasing your background radiation. Do you live in a brick or a stone house? Because if you live in a brick or a stone house, they will ultimately release radon, which will increase your background radiation. Do you live near a power station? That's a man-made background radiation source. Have you had many x-rays? I mean, have you broken your leg 17 times? In which case, you will be exposed to more radiation than most people. And maybe you're a seasoned traveller. Maybe you go to Canada 7 times a year. That will affect the amount of background radiation you have as well. And perhaps you like prawns. Perhaps you love Brazil nuts. Those things will affect how much you are affected as well. Now, I don't want you to worry, okay? Because you could live in Cornwall, eat a diet of pure shellfish and Brazil nuts, and you could fly 100 times a year. You still wouldn't be in any great danger, I guarantee it, okay? But what you can do is download a little sheet below me, and you can work out what your background radiation is. And it will give you a value in sieverts. That is what we measure background radiation, or your radiation dose in. And it's usually millisieverts. It's usually so small that it would be 1,000th of a sievert that you would be measured in. You're in no danger. If you were in danger, you would know about it. So, in fact, whilst we have background radiation around us all the time, it's not of a level that you would need to worry about, unless you did live near somewhere like Chernobyl. So let's go to our revision notes in our definition section. Let's put our background radiation definition, and that is defined as low-level radiation around us all the time. And then in the other notes section, can you write down the factors affecting the level of background radiation? The sheet below us will help you with that, but you're really looking to include things like flights, live in a stone house. Do you live near radon rocks? Things like that. Things that affect, shellfish. Things that we talked about that affect your level of background radiation. Let's go and pop these things into your other notes.